Okay, let's remember where we left off. We had talked about a line search, and remember the algorithm we're using for unconstrained optimization. We have some point that we're at, we pick a search direction, then along that search direction, we have a one-dimensional problem to decide what the appropriate step length would be. As we talked about, we'll find a point that's just good enough. We're not going to try and find the best point there, just something that's good enough. And we'll move to that new point, pick a new search direction, and just keep repeating that process till we converge. So we've talked about how to do that line search portion. And while we were doing that, we said we could guarantee that the search direction was a descent direction, but we didn't talk about how to actually choose one. So that's what we're going to talk about today, how to choose a search direction. And we won't actually be able to talk about all of the approaches today, but we'll talk about a few. All right, I'm just sharing my screen real quick. There we go. All right, search directions. So here is an algorithmic form what I just said. It's this process that we're going to repeat in a loop. First, we pick a search direction, which is going to be a descent direction for a minimization problem. We'll then do a line search to choose what step length. This is a scalar, right? This is a vector. And then we take our current point and we add the length times the direction to get our new point. And we update the iteration and just keep doing that over and over until we satisfy some convergence criteria. In this case, our first order optimality condition that the norm of our gradient is going to be less than or equal to some tolerance, and we would exit this loop. Okay, so how can we determine a search direction? Think back to what we discussed in some of the earlier lectures. How would we find a descent direction? Take a moment and think about that. Pause if you need to. Here's a reminder of one of the figures we looked at before. These arrows that we're showing here are what's known as the gradient vector. And remember, the gradient vector always points in the direction of steepest increase. So if I'm at any given point in my function, right, there's a bunch of different directions, infinite number of directions I could go. And the gradient, by taking those partial derivatives, that gradient will tell me which way increases the fastest. So if I want to go into the fastest decrease, just as you might expect, it's the negative of the gradient. That opposite of that gradient will point me in the direction where my function is decreasing the fastest. Okay, so that seems like a good strategy that we should adopt. That we should go pick our search direction to be the negative of the gradient. We call this steepest descent, right? Because it's the steepest descent. It's a descent direction that's going to be the steepest. So our search direction, and P we're using for direction, is the negative of the gradient of our objective. Again, the gradient of the objective points in the steepest increase, so the negative of the gradient points in the steepest decrease. And depending on how we define our search length, we might want to normalize it. So sometimes we'll do it this way. Right? We'll take the gradient and then divide by the norm. That would just make this a unit vector for our direction. Okay, but either could work. We just come up with different step lengths. All right, so this seems like the best possible thing we could do, right? Because it's the steepest decrease. So let's see how it looks. Here we're taking a quadratic function. It's just a simple function so we can visualize it. And we're putting the scalar beta just so we can change the function a little bit, try different cases. So first we have beta equals 1. Here's my starting point, x naught. Boom, one iteration, I get to the optimum. So just as we expected, steepest descent is awesome. Gets us there really quickly. So now let's increase beta. Okay, so now beta is a bit higher, and notice what happens to the level curves, right? They're more stretched out, so it's not a circle anymore. When beta is 1, they're all equal. Beta, I think it's 5 or something in this case. They're stretched out a bit more, okay? And now we see that steepest descents, it's maybe zigzagging a bit. It still gets there, but it took 32 iterations. Let's make beta even bigger. You can see these become more stretched. And now it takes 111 iterations. And you might notice this pattern that we're starting to zigzag a lot. So this is a general takeaway with steepest descents. It seems like it's the best possible approach, and maybe it's somewhat counterintuitive that it actually isn't always that effective. Um, it works really well if the curvature is the same in all directions. Okay, so if we were to take the Hessian, the second derivatives, it would be like the diagonals were all the same, right? It'd be like an identity matrix or a scaled identity matrix. Whereas in these cases, the curvature is very different in one direction versus the other. And in that case, the steepest direction actually causes us to zigzag as we go back and forth. And so it can take actually a really long time to converge. And unfortunately, almost every interesting problem is going to have more complicated curvature than this. And of course, won't be just a quadratic, it's going to be some highly dimensional thing. And so in practice, steepest descent actually is usually pretty ineffective for a lot of these design problems. Now, there are cases when it can be effective, and we'll talk about some of those later, but later in the semester. But in general, it's often not a very effective method. We can actually prove that these steps are going to be orthogonal to each other. Now, let's say, and so if we did a line search or an exact line search, we actually won't know where we hit, right? It would depend on whatever criteria we use. But just for the purpose of an example, let's say we did the exact minimum every time. So we picked our search direction, found the exact minimum in that direction. You know, if we could do it cheaply, right, that might be the best thing to do. So let's just do the exact just to motivate this. So if I was doing the exact search, right, remember my next step, right, so I'll just write it out explicitly. My next step, right, is going to be, oops, my previous step plus my step length times p, right? We're just going to get used to that. We're going to be using it a whole bunch of times. So I want to choose the optimal alpha here. So I want to choose, so I'm going to take the derivative and set it equal to 0. That helped me pick the best alpha. So I want my function at that point, right? I want to evaluate that function, and I want the derivative with respect to alpha to equal 0. In other words, I'm choosing the alpha that's going to maximize or minimize rather my objective, okay? And actually, well, actually I'll just keep the k's. This is really with respect to xk then, alpha k. All right, I could also write that this way. This is a derivative with respect to x of k plus 1 with respect to alpha k, right? And by the chain rule, I could say that equals the partial of f xk plus 1 with respect to x of k plus 1 times x, the derivative of x of k plus 1, but instead of x of k plus 1, I'm going to write this part, just doing 2 steps in one here. X of k plus alpha k pk, and then by the chain rule, this is going to be with respect to alpha. Okay, and if you've forgotten the chain rule, I'd encourage you to again look at the appendix kind of math review there. But again, if the 2 steps was too confusing, right, put this in first, x of k plus 1, right? So you could think of those canceling out, so to speak, roughly speaking, right? So then these would be the same. That's kind of a rough way to say it, but anyway, so let's take these derivatives. This first derivative, the derivative of x of f of x with respect to x, that is the gradient, right? This term here, that's the gradient at k plus 1. So that says the gradient of f at k plus 1. And this term here, I'm taking the derivative of this term with respect to alpha, that's just going to give me p. Okay, so this is a vector, so I need to put a dot product. This is p at k, and that's going to be equal to 0. But our choice of p, remember, what is our choice of p? It is the gradient of f, right? So, or it's actually the minus the gradient of f. So this becomes minus p of k plus 1 dotted into p of k equals 0. So what does it mean when I take 2 vectors and their dot product is 0? Right, this is the step length at my last iteration. This is my step direction at my current iteration. Sorry, both step directions. The dot product of those 2 is 0. Remember, if the dot product is 0, it means those two vectors are orthogonal. So that means the step direction I went, right, P of K in my current step, my next step, K plus 1, is going to be perpendicular to that. So I'm going to get this zigzaggy behavior. Now, as we talked about, we don't actually do an exact line search, so we don't actually optimize this to find the minimum and find the exact optimal alpha. So it's not going to be exactly orthogonal, but even in general with an exact line search, we still get this kind of zigzagging behavior. Again, not perfectly orthogonal, but still very slow and kind of back and forth because of these changes in curvature where, say, one direction maybe has a gradual curvature and one's very steep. The steepest direction has me going this way and then back and then back and then back and then back. So it can take a really long time to converge. Well, if we do want to use this method though, or I should say another limitation of this method is that while we had a very obvious choice for what the direction should be, it's not really obvious what alpha we should use as our initial guess. In other words, what should the initial step size be? There's not an exact answer to this, but a method that can be effective is to use an alpha that's going to give us a step length that was similar to our previous step. So the intuition there is that one step to the next isn't going to have drastic changes. So if we knew what a good step size was previously, the next step should be similar. Not the step in alpha, but the total step. So in other words, the change in our function should be similar. And the change of our function is going to be the gradient at some iteration. This is our directional derivative dotted into our step, which is going to be alpha k pk. Right? My assumption here, or our assumption here, is that that change, that directional derivative, the amount of decrease that we get at a given iteration, should be similar to the decrease we got at the previous iteration. So then we would say the gradient of f at k minus 1, alpha of k minus 1, p of k minus 1. And again, if you go back and look at a directional derivative, this is the directional derivative. It's how much our function is expected to decrease. So we're expected to decrease a similar amount in this next iteration, or let's choose an alpha that gives us a similar decrease. That's just the thought here. So alpha is a scalar. We can pull it out of this dot product here. And p, remember p, right? P is just the gradient of f. It's really the minus gradient of f. K, right? So I've got the dot product. I could write those as the norms. I'm going to get the same thing over here. The negatives are going to cancel out. So I'm going to get, just doing this in one step here, alpha of k is equal to alpha of k minus 1 times the gradient of f at k minus 1, k minus 1. I'm taking the norm squared and then dividing by the gradient of f k squared. Let me write that better. Okay, so this is an update formula, right? This is not, I shouldn't say really a formula, it's more of a heuristic. This is just an approach that tends to work pretty well because we have no other way, or we don't have any way to provide a super intelligent guess. So this is just something that says, this is what we got previously, it worked out, we accepted the step, so this is probably about a reasonable scale of a step to take. Just by way of review again, if this notation, if you've forgotten a little bit of linear algebra, remember that if I took the dot product of two vectors, say x transpose x, that's the same as the norm squared, right? Or if I was to write these in components, let's just say this would be like, let's say it was x1, x2, x3. Let's just say I had 3 dimensions. That was my vector x. So you can see the dot product, x transpose x, is going to give me x1 squared plus x2 squared plus x3 squared, right? And this norm squared, remember the norm is going to be, the norm is the square root of the sum of the squares, x1 squared plus x2 squared plus x3 squared. But then I square the whole thing, so of course those things cancel out and I have the same expression. So that's how that's what happened in that step there. So again, what I need to do here, I need to look at what my last step length was, and I just need to save the gradient. Save the gradient for my last iteration. I'm going to compute it again at this iteration. I just use this little update formula, and that gives me, not again, not really a formula, but a reasonable way to kind of provide a starting point. Again, this is not the alpha we're going to use necessarily. It's just the starting point that we're going to use to go into the line search. And then we may need to backtrack or do a more sophisticated line search from there, but it gives us a starting point. Okay, so we're going to look at these different methods on the same function here. This is the bean function, or actually that's what we call it. We just made it up. It's a function that has a little bit of curvature to it, but it's not terribly complicated. And here's steepest descent. It actually was pretty fortunate. This right angle here actually lined up pretty well based on the starting point to get us pretty close. But then, even though we're really close, because it has to zigzag a lot, it takes quite a while to converge. But it worked okay. All right, so steepest descent, not the greatest. The main problem, as we said, is it tends to want to overcorrect too much. The steepest direction is not actually necessarily the best, even though that feels like an intuitive thing to do. So let's look at the next method. You might be thinking to yourself, well, I don't want to turn so sharply, right? So maybe I can dampen that a bit. And there are actually quite a few methods that try to do that. We'll talk about one here, a classical method here called conjugate gradient. And first I'll motivate with the linear conjugate gradient. And the basic idea is fairly straightforward. And the idea is this. Imagine I have, let's say, a simple case where I have just a quadratic function. And this could be a quadratic function in any number of dimensions. We can, of course, visualize it easily here in 2, but it could be any number. And let's say that the Hessian is a scaled identity matrix, meaning the curvature is the same in every direction. Okay, so that means our level contours are going to be circles. We could also say the condition number of the matrix is 1, if you remember that from linear algebra. In any case, it's going to look something like this, right? Circles, or in higher dimensions, spheres, hyperspheres, whatever. So the idea is that wherever we start from, we could take our coordinates one at a time and search along that coordinate and find the minimum along that direction. So let's find a minimum going along this x1 direction. Once we do that, we fix x1 and we find the minimum along the x2 direction. And as long as our contours are all perfectly circular like this, we have an identity matrix basically for the Hessian, or constant times the identity matrix, then we will always reach the minimum in n steps. So even in 10 dimensions, n is 10, we would reach the minimum in 10 steps. So that's great. We can provide a bound here and we can get there pretty efficiently. Of course, our functions aren't going to look like this, so we can actually generalize this a little bit. Imagine we still have this quadratic, but the condition number is not 1, so there's some skewness here, right? The curvature varies in one direction versus the other, and we might rotate it. So it's more like the problem we saw before, right? Where the steepest descents actually struggled. What we could do is we could use a similar concept and choose directions that are not orthogonal. Here they were orthogonal to each other, right? But they're orthogonal in some other sense. They're orthogonal in this curved sense of the space. We call these conjugate vectors, and mathematically we'd write it like this. So the direction, let's say I had pi, and here's my Hessian matrix. Yeah, and then pj. So this is a scalar, right? I've got a row vector times a matrix times a column vector. That gives me a scalar. If this equals 0 for all I not equal to j, then we would say that these two vectors are conjugate vectors. You could think of it as a generalization of orthogonal vectors. So if we went back to the last case, remember where the Hessian was an identity, or the constant times an identity. If this was an identity, then we just have the dot product of these two vectors. They're 0, so that means they're orthogonal. This is a generalization where the Hessian now has some curvature. It's not the identity. Not every direction is the same, right? There's some skewness to it. Some directions are curved more than others. So in other words, maybe some terms in the diagonal are bigger than others. There's some off diagonal terms, perhaps. But if this is true, right, if we can find these vectors, then the nice property is for this quadratic, we can still get to the minimum in n steps. So in 2 dimensions, you can get to the minimum in 2 steps. In 10 dimensions, we can still get to the minimum in 10 steps. Okay, so again, we're finding these vectors that are not orthogonal in the classic sense, but orthogonal in this sort of stretched sense, and they're orthogonal with respect to our curvature, which is captured in that Hessian, our second derivative. Okay, so that's the idea. Of course, we still don't have quadratics, but we have more general nonlinear functions, but we can use that same kind of idea in an iterative way. We use these conjugate directions, and what happens is that we periodically do a restart. So we use conjugate directions and periodically restart and go to a steepest descent. But I won't go through the derivation here, but just show you the result. And the end result is fairly simple. It's this, that our current search direction is going to be the negative of the gradient. So far, exactly the same as steepest descent. And we're just going to add one term to it. We're going to add beta, which is a scalar, times our previous step. Okay, so you could think of it this way. We're taking the steepest descent direction, but we're dampening it a little bit. We're not going quite as far as we would have. So for example, if this was P of k minus 1, and maybe our steepest descent, it wanted to take us, perpendicular to that way over there, and it's going to zigzag too much. We're going to dampen it a bit. We're going to add, right, some fraction of, here's P of k minus 1. I'm going to draw it over here again. Right, I just moved it over. That's P of k minus 1. I'm going to add some fraction of it. So if I make beta, I multiply by beta, which is some smaller number. So I'm going to dampen it. So instead of zigzagging quite so harshly, that's not a right angle, like this, I'm going to be going, a little bit straighter, right? Not quite as much zigzagging. Okay, that's maybe some intuition there. Okay, so beta is also given for us. It just depends on these gradients. So let's see, it's the gradient. Actually, I'm going to write it as a norm, a little different than I wrote it in the book, but it's the norm of gradient squared divided by the norm of the gradient of the previous iteration squared. Okay, so it's not too different from the last method, especially if we're using the way to select a step size. All we have to do is save our last gradient. Then we can update beta. We also saved our last search direction, and we can compute a new one. So, it takes maybe another line of code, maybe a line or two, as compared to steepest descents. Not that much more complicated, but generally gives us a significant improvement. So here it is on the bean function. It actually isn't as dramatic in this case because steepest descent was pretty lucky in 2 iterations where it got. So it's a little more gradual here. It's not quite as aggressive, but that was, again, a bit fortunate just because the shape of these contours happened to be about a right angle to get us close to where we wanted. But it converges much faster here, and we saved quite a few iterations. In this case, I think it was 34 before steepest descent. And this, of course, will vary problem by problem. We'll look at a bigger problem next time when we look at all these methods together. Okay, so that's the second method. A third method. So far, we've talked about methods that use the derivative. And in all those cases, we talked about curvature. We talked about, well, curvature is a challenge, right? Curvature varies from one direction to the other. So we could probably do a much better job if we use that curvature information directly. Or in other words, we use information about the second derivative. And this is not new. We talked about this a couple times actually, but in the numerical methods lecture, we talked about Newton's method. So this will be the exact same derivation we looked before. I think before we did an index notation, he'll be using vector notation, but same idea. Newton's method is, let's imagine that I have my function f of x, right? And I want to take some step s, and I want to choose the step that's going to give me, that's going to, let's say, minimize my function, or usually we'd say it in terms of finding a root, right? But here we're going to talk about in terms of finding minimization, which would be related to finding the root of the derivative, right? When the derivative equals 0. But first, let's just do our Taylor series. So here I am at step k. Actually, I'm going to drop k because everything here on here is going to be at iteration k. Okay, so I'm taking some step s. I don't know what s is yet. That's going to be equal to f at that iteration, f of x, plus the gradient of f of x times my step length, plus 1/2 times my step length times the Hessian times the step length plus higher order terms. Okay, so that's just the Taylor series that we've seen. All right, so if I want to find a step length that minimizes this function, how do I do that? I've done this a bunch of times now, right? This is just, we take a derivative, set it equal to 0. Okay, so let's try that. Let's take the derivative. Take the derivative of this thing with respect to s and set it equal to 0. So the derivative with respect to s, this first term has no s's. This term here just returns the gradient of f, the gradient of f. And then this term here, this may not be obvious to you, but there is also a review of this this quadratic form in the appendix of the book, but it's gonna give me this, the Hessian times s. If you want to think about the 1D case, right, this would be like having a 1/2 s squared times, we'd call this f double prime, right? And so when we took the derivatives, that second derivative, the 2 would come out and cancel, right? And then I'd get a first derivative. Anyway, it's the same kind of idea here, but with a matrix. Did I say that right? Yeah, sorry, not the second derivative. So if this was a 1D case, we would write like this, right? 1/2 s squared f double prime of x. And then we took the derivative with respect to s, right? We get a 2s times the 1/2, and those cancel, right? So it's going to be s times that second derivative. That's not really a perfect analogy here. It's worked out more formally in the appendix, but this is what we get, same idea. Okay, and so we were trying to solve this for s. So I could also write this way, hs equals minus grad f. This is a matrix, vector, vector. So this is a linear equation, right? ax equals b. And we would solve it as a linear equation. Mathematically, we could write it like this, h inverse times grad f. We wouldn't do that in a computer because, as we talked about, taking an inverse is expensive on a computer, but solving a linear system is going to be much more efficient. So we would pose this as a linear system solve, but mathematically, this is the idea. And this is exactly what we derived before. So this is nice. This is a method we could use. Notice though, we're going to need more than just a gradient. We're going to need a Hessian. But if we have a Hessian, if we have those second derivatives, this provides us a really good guess for a search direction. And notice this is why we wrote S instead of P. It's more than just a search direction. It's a direction plus a length. So we'll often call S is kind of that combination of alpha and P. So this gives us a good guess for a place to start, because this is the full vector. It's not just a direction. It's like, this is the place where we think we're going to minimize at least a local quadratic. It's not going to be perfect because our function isn't, or usually isn't actually quadratic. So this is just a Taylor series approximation, but in a neighborhood, this should be a good guess about where to go. Okay, so we now are using curvature information explicitly, so we'd expect we could do much better. In fact, as we talked about with Newton's method, this has quadratic convergence that can be very efficient. And in fact, if we had that quadratic function, we'll get there in one step. Remember the one that we saw with steepest descent? This guy here? We can make beta whatever we want. And if it's quadratic, we'll always get there in one step. Even in this case, with 111 iterations, even if we skew it even more, because we have that curvature, that second derivative, one step every time. So that's awesome. But of course, again, real functions, most of our real functions aren't quadratic. They're going to be more complicated than that, but we still expect it to do better. And indeed, that is generally the case, right? So here, the curvature, leads us a bit off to begin with, but it gets us very quickly, converges very quickly here in 8 iterations. So very efficient. Okay, so this is an awesome method, or at least sounds like an awesome method, but it has some problems. There's 3 kind of big problems here. Okay, so here's problem 1. The Hessian might not be positive definite. And remember when we talked about positive definite, that means, we could think of it conceptually as it gives us that bowl shape. So what that means is that this search direction that it returns might not be a descent direction. And that's a problem because remember we said we're going to guarantee that our search direction is a descent direction. Okay, so that's a problem, but there are actually some techniques we can use to deal with it. We know that descent directions exist, right? We talked about this, the directional derivative. As long as we're not at the minimum, there's always a descent direction. So we know it exists, and there are techniques to modify the Hessian to maybe find, for example, the nearest matrix that is positive definite, but that's closest to the Hessian. So we can modify the matrix, for example, to find something that's close, that still captures that curvature information approximately, but at least puts us in a descent direction. So there are things we can do to deal with that. The second point is that the new point, the predicted point, boy, that's horrible. I'll just call it the new point. The new guess, x of k plus s of k. Notice I didn't write an alpha there because this is giving us a full step. The new guess might be bad. Okay, we predicted that this is the minimum of a quadratic. And if our actual function was quadratic, we'd be right on. If we had the correct Hessian, be right on, get there in one step. But our local function, like this being, is not actually quadratic. So we've got maybe some approximation of a quadratic here. If I was just to guess, and let's just draw like some curves here, maybe it looks something like this, right? The local quadratic. Well, I guess that's not what it looks like because it went over here. So it's hard for me to tell because the curvature is changing so much here, but yeah, maybe it must have looked something more like this. Anyway, whatever it was, it might be a bad guess. So it might take us somewhere that we thought was really good, but it's not. But this is also easy to address. And in fact, you know the solution to this. How would you address this? Take a moment to think back. So this was the idea of the line search, right? That the initial point might not be good, but we know if we backtrack enough, right? If we backtrack enough, this Taylor series here is going to become a better and better approximation, right? Because it was about this point. So if we go back further, then this is going to be a good approximation or better and better. And eventually we know it's going to give us a descent direction, at least, especially if we did this first step, right? Or at least if we have done this, if we had to do this first step. So we know if we go back, we will get a descent direction. So that's not too bad, right? So far we've had a couple problems. We can modify it. There's some techniques to do this. It's really an optimization problem of its own, but we can find analytic solutions. That's not too bad. We're not going to take this step. So what we're going to do is we're going to say, okay, rather than just saying, let's just accept it. Let's take P, or sorry, let's take S and make that P, and we'll make our initial alpha to be 1, right? So often it will be a good guess and we'll just take alpha to be 1, but we might have to backtrack. Okay, so 2 problems taken care of. Third problem though, is that the Hessian is actually often a pain to get, right? It can be difficult to provide, difficult or expensive, costly to provide, okay? So sometimes we can do this analytically, but often just getting first derivatives is a challenge enough, and getting second derivatives can be problematic. And if we're doing things like finite differencing, that can work pretty well for first derivatives often, but second derivatives where we're doing an approximation of an approximation to get a second derivative, those tend to be not very good, often really poor. So for many engineering problems, we actually can't really provide a good Hessian. Now, there's some techniques to do this with better accurate gradients that we'll talk about, but even in those cases, providing the Hessian can still be fairly expensive, right? Because remember, the gradient has n terms, and it's especially problematic as my problems become larger. If I've got 100 variables, my gradient is still just a vector of n, but my Hessian is a matrix, so it's scaling with n squared over 2, but still that sort of n squared scaling. So as my problems become bigger and bigger, it becomes much more costly to provide that. And so this is a fundamental limitation, unavoidable for Newton's method. So we're going to have to find an alternative. And this is what we're going to talk about next time. We're going to talk about these quasi-Newton methods that we're going to use the ideas of a Newton method, but we're going to do it in a way where we don't actually need to provide the Hessian. We're going to try to build up our own estimate of the Hessian. That's going to take a little more to develop, so we're going to save that for next time. So we'll end with this today and look forward to getting into those details next time.